Take an ordinary pane of glass, nothing fancy, like the kind in a window, and shine a beam of light straight at it. Most of that light passes through without trouble, but a small fraction doesn't. Roughly 4% of the light reflects back towards you. Out of every 100 photons that strike the glass, about 4 reverse course. That's the strange part. How does a photon make that choice? You send in 100 photons that are completely identical, arriving at the same surface, from the same direction, with the same energy. 96 continue onward, 4 are reflected. Why those 4? What sets them apart? It's tempting to think the glass must have tiny flaws, microscopic bumps that bounce some photons away, and gaps that let the rest through. That explanation feels sensible, but it isn't correct. You can manufacture glass that is smooth and uniform down to the atomic scale, and you still get the same 4% reflection. The photons aren't reacting to defects. They're doing something far stranger than bouncing off tiny imperfections. So maybe the photons themselves aren't truly identical after all. Maybe each one carries some hidden mechanism, a tiny internal dial or timing wheel that decides whether it reflects or goes straight through. It sounds absurd at first, but it's not an unreasonable guess. There's just one problem. An experiment wipes that idea out completely. Take a sheet of glass that's extremely thin. So thin it's basically a film. Now light encounters not one surface, but two, a front surface and a back surface. If each surface reflects about 4% on its own, you'd expect something close to 8% total reflection. 4% from the first surface, roughly 4% from the second. Simple math. But that is not what happens, not even remotely. Depending on the exact thickness of that glass film, the reflection can be anything from 0% all the way up to 16%. 0 to 16. Same material, same light, nothing changed except thickness, and the amount of reflected light swings from nothing at all to 4 times what you'd expect. So how can that even work? How can introducing a second surface sometimes erase the reflection from the first one entirely? It almost feels like the rear surface of the glass is reaching backward through time and instructing the front surface not to bounce the light at all. And if you keep increasing the thickness of the glass, this strange behavior doesn't stop. The same pattern shows up again and again, perfectly spaced, perfectly predictable. With sufficiently precise instruments, you can watch this cycle repeat millions of times. Millions of times. This isn't a tiny curiosity or a lab trick. This effect sits right at the core of how light actually works. So what is actually happening here? This is the point where things stop being merely odd and start becoming deeply unsettling. The explanation that works, the one that lines up with every experiment, is that light never commits to a single route. It doesn't choose to reflect or to pass through. Instead, and this is the part that sounds completely unreasonable, light follows every possible path at the same time. When a photon reaches the glass, no decision is made. It reflects off the front surface, it goes through, it reflects from the back surface, and it passes through both surfaces simultaneously. All of these possibilities occur together, overlapping in a way that defies everyday intuition. But hold on, if all outcomes occur, why do we ever see a single clear result? Why does a detector either register a hit or stay silent? This is the crucial part. Every possible path carries what physicists call a probability amplitude. You can picture it like a tiny arrow attached to each path. These arrows have directions, and that matters. When you combine them, arrows pointing the same way reinforce each other and make the outcome more likely. Arrows pointing in opposite directions wipe each other out. So when light passes through a thin layer of glass, the arrow for reflection from the front surface and the arrow for reflection from the back surface can line up. Add them together and you get a large arrow, meaning a high chance of reflection, 16% instead of 8%. Change the thickness just a little, and those arrows can end up pointing opposite ways. They cancel exactly, no reflection at all. The contributions from the front and back surfaces interfere destructively and effectively erase each other from reality. And this idea isn't limited to glass, it applies to everything. Mirrors, lenses, rainbows, the blue of the sky, the shine of metal, the transparency of water. All of it comes down to those tiny arrows either reinforcing one another or cancelling out. All of it depends on light sampling every possible path at once. The framework that captures this behavior is the most accurate theory science has ever produced. Its predictions are correct to 12 decimal places. At that level of precision, you could measure the distance from Los Angeles to New York and be off by no more than the width of a human hair. That's how powerful it is. And yet, if you ask a physicist why light behaves this way, why it explores all paths, why probability is governed by these arrows, there is no deeper explanation. Not because no one has tried. They have. Brilliant minds across generations have pushed on this question. The honest answer is that we don't know. This is simply how nature operates. Consider an ordinary mirror. You were probably taught that light reflects off it by a simple rule. The angle it arrives equals the angle it leaves. That part is correct, but it doesn't explain why it works. The usual story is that light moves in straight lines and rebounds like a rubber ball. In reality, light reflects from every point on the mirror, not just the central spot where the angles line up. Every location matters. The edges, the corners, even the far left side of the mirror. Light reflecting from those regions is completely real. It exists and it happens. So why do we only observe a clean reflection from the region where the angles match? The answer is the same arrows again. The paths coming from the middle of the mirror take nearly the same amount of time to travel from the source to your eye. Their arrows end up pointing in almost the same direction. When you add them together, they strengthen each other and dominate what you see. But the paths coming from the edges take noticeably different amounts of time to reach your eye. Because of that, their arrows rotate and end up pointing in all sorts of directions. One tiny region contributes an arrow pointing one way, the next contributes one pointing the opposite way. When you add them together, they cancel out. The edge contributions effectively vanish, and this isn't just a theoretical idea, you can demonstrate it. If you take a mirror and carefully remove parts of it, not at random, but in a very specific pattern, eliminating the regions that would produce arrows pointing the wrong way, something strange happens. The edges of the mirror suddenly begin to reflect strongly at angles that should never work. This is exactly how a diffraction grating operates. It's essentially a mirror with most of its surface blocked in a deliberate pattern, so that destructive cancellation no longer wipes the signal out. So light isn't following the law of reflection at all. It doesn't know that the incoming angle is supposed to match the outgoing one. It simply spreads out in every direction. The math of those arrows combining just makes it appear as if a clean rule exists. The same idea explains why light bends when it enters water. It's not because light understands that it should slow down and change course. Light simultaneously tries every possible path through the water. The paths where it bends by the wrong amount cancel out. Only the paths where it bends by exactly the right amount, what we call the law of refraction, survive because their arrows align. Sit with that for a moment. Every neat rule about light you memorized in school is actually the surface result of something far deeper and far more bizarre. Light explores all possibilities, and the familiar laws emerge from interference between them. This is one of the great discoveries of 20th century physics, and honestly, it has never fully made intuitive sense to anyone. You can compute with it flawlessly. You can build lasers, fiber optics, and entire technologies on top of it. But truly understanding it, feeling why reality behaves this way, that part still slips through our fingers. Alright, now we have to push further because everything so far has only been about light reflecting and interfering with itself. But light doesn't just bounce around, it interacts with matter, specifically with electrons. And this is where the story becomes even stranger. Here is what we know with absolute certainty. When it comes to the interaction between light and matter, the entire universe really only involves two kinds of particles, just two. Photons, which are particles of light, and electrons, which are particles of matter, the components that make atoms behave the way they do. That's it, two actors on the stage. And everything you can see, every color, every shine, every shadow, the very fact that vision is possible at all, comes from these two particles performing an astonishingly simple dance together. There are only three things that can ever happen, three fundamental moves, and that's it. First, a photon can go from one location to another, simply traveling through space and time. Second, an electron can move from one place to another. Same idea, just a different particle. And third, which is the crucial one, an electron can absorb a photon or release one. Three actions. That's the entire menu. Everything else, without exception, is built from these three events repeating in different sequences. Consider what that really implies. When you look at a red apple, what's actually going on? Photons from the sun strike electrons on the apple's surface. Those electrons take in the photons, shift their motion, and then emit new photons. Because of the way the electrons are arranged in those molecules, red photons are emitted more often than blue ones. Those red photons travel to your eye, are absorbed by electrons in your retina, and set off a cascade that eventually becomes the sensation of red. Every step, from start to finish, is just those same three actions happening again and again. Now we arrive at the mathematical part, not in a heavy or technical sense, but in a way that's genuinely unexpected. Each of those three basic actions comes with a number attached to it, a probability, amplitude, one of those little arrows we've been talking about. When a photon travels from point A to point B, there's an arrow that represents that process. When an electron moves from A to B, there's another arrow. And when an electron absorbs or emits a photon, there is an arrow for that interaction as well. What's remarkable is that the interaction arrow is always the same size. Always. It never changes. It's a single fixed number, about 0.1. And if you prefer to think in terms of probability, you square it and get roughly 1%. 1 chance in 100. That number is, honestly, one of the deepest mysteries in all of physics. It appears everywhere. It determines the strength of the electromagnetic force. It decides how tightly atoms bind together. It sets the scale for all of chemistry and by extension for matter itself, and no one, truly no one, knows why it has the value it does. We can measure it with astonishing precision. Its value is about 1 divided by 137, roughly 0.0073. Physicists give it a name, the fine structure constant. But naming it doesn't explain it. Ask why it has this value instead of some other number and the room goes quiet. You might get a shrug, a speculative idea, but no real answer. It's like asking why light travels at the speed it does, or why the electron has its particular mass. These are quantities we can measure perfectly, and yet cannot justify. They are simply features of reality, raw facts about the universe that so far refuse to yield any deeper explanation. So now you've got these three basic actions and their arrows, and the way you predict what actually happens with light and matter is surprisingly visual. You literally draw pictures. Not casual sketches, but very precise diagrams. You map out every possible way an event could unfold using only those three moves. A photon travels, meets an electron, the electron shifts, emits another photon, that photon moves on. Every possible chain you can imagine. For each diagram, you calculate a single arrow by multiplying together the arrows for every step in that picture. Photon moving, multiply its arrow. Electron moving, multiply its arrow. An interaction occurs, multiply by that fixed 0.1. Once you've done this for all possible diagrams, you add all the arrows together. Just like with mirrors and glass, some arrows strengthen each other, others cancel out. The final arrow you're left with gets squared, and that number is the probability of the outcome you observe. Every time an interaction appears, an electron taking in or giving off a photon, you multiply by that small factor, about 0.1. So a diagram with a single interaction carries a factor of 0.1. Two interactions give you 0.1 times 0.1, which is 0.01. Three interactions drop it to 0.001. As the diagrams get more complex, their contributions shrink rapidly. That's why prediction is even possible in the first place. The simplest diagrams dominate. The more tangled ones matter less and less. Most of the infinitely many possibilities can be safely ignored because their arrows are simply too small to have any effect, but not all of them, and that's where the astonishing precision comes from. If you want extremely accurate answers, you must include increasingly complex diagrams. Each adds a tiny correction. Add up thousands of those tiny corrections, and the final result matches experiments to 12 decimal places. 12. That's like measuring the width of an entire country, and being off by no more than the thickness of a human hair. No other theory in science comes anywhere near that level of accuracy. Now here's the part that sounds like it should be forbidden, yet it works perfectly. In these diagrams, photons are allowed to do things that seem completely impossible. They can move backward in time. They can travel faster than light. They can even carry negative energy. That sounds insane, so how is it allowed? The answer is that these strange photons are never directly observed. They're known as virtual photons. They exist only as temporary steps inside the mathematics. A real electron over here emits a virtual photon. That virtual photon does something outrageous, like moving backward through time. Then another electron absorbs it. What you actually observe at the end is simple and ordinary, just two electrons repelling each other. The virtual photon itself is never seen. You can't detect it, you can't isolate it. It exists purely as a mathematical tool that makes the interaction come out right. And here's the truly strange part. You can't leave those impossible paths out. If you only include the diagrams that look reasonable and well-behaved, the answers come out wrong. The theory only succeeds when you allow photons to do utterly bizarre things in the middle of the calculation, even though the final result is always something completely sensible and physical. This is what physicists mean when they say nature is absurd. Not absurd in a sloppy or chaotic way, absurd in a sharply defined, tightly constrained way that produces answers of astonishing accuracy. The rules sound insane, but they work flawlessly. Ed? This is the question that sits at the center of everything. Why these rules and not others? Why does the interaction have exactly this strength? Why do the arrows combine in this particular way? Why does probability come from squaring the arrow instead of some other operation entirely? No one has answers. These questions have been on the table for nearly 100 years. Generations of the sharpest physicists have struggled with them, and we are no closer to a final explanation than we were at the start. The theory works. It is the most successful framework humans have ever built, but explaining why it works at such a deep level remains beyond our grasp. There's a quiet kind of integrity in admitting that science isn't about acting like we have all the answers. It's about being exact about what we understand and honest about what we don't. We know how light behaves. We can compute its behavior with staggering precision. Why it behaves that way is still unknown. Maybe one day someone will uncover the reason. Maybe the explanation is hidden in an equation that hasn't been written yet. Or maybe some things simply have no deeper reason. Maybe asking why is like asking why the number 3 is odd. It just is. Until we know, we keep calculating, we keep experimenting, we keep pushing the accuracy further and further, searching for even the smallest flaw in the theory that might reveal what lies beneath. So far, there are no flaws, just this strange, elegant, utterly absurd picture of light taking every possible path at once, and the mathematics unfailingly delivering the correct answer. So let's pull all of this together, because there's something genuinely disturbing about where this leads, and it's worth pausing with that feeling. We began with a simple question: how does light actually work? And the answer we arrived at was that light simultaneously explores every possible path. It doesn't pick one, it doesn't make a decision, it simply does everything at once, while the mathematics of interference determines what we end up observing. That alone is strange enough. But then we went further. We discovered that every interaction between light and matter reduces to just 3 fundamental moves. A photon travels, an electron emits or absorbs a photon. That's the entire story. And these actions combine through rules built from tiny arrows, probability amplitudes that add together or cancel out, producing predictions that match reality with perfect reliability. When this picture really sinks in, it leads to something unsettling. The world we think we live in, a world of solid objects, clear events, and light moving neatly along straight paths, turns out to be a kind of illusion. Not an illusion because it isn't real. It is real, but it emerges from something far stranger beneath the surface. At that deeper level, there are no straight lines. There are all lines, every possible path unfolding at once. There are no definite outcomes until a measurement happens. Only amplitudes, only overlapping possibilities layered on top of each other. The familiar classical world is what appears when trillions upon trillions of these quantum events are averaged together. The arrows pointing in all directions mostly cancel out. What remains is the orderly, intuitive behavior we recognize. And that intuition isn't fundamental. It's just a consequence of scale. At our size, the strangeness stays hidden. This isn't a gap in our understanding waiting to be filled. It's not that we simply haven't uncovered the deeper machinery yet. As far as anyone can tell, there is no deeper layer. The quantum description is the foundation. The arrows, the interference, the probabilities, that's what reality is made of. You might want to believe there's some hidden variable we've missed, some unseen clockwork deciding in advance which photon reflects and which one passes through, restoring the neat determinism of classical physics. People have searched for that for nearly a century. They really have. Physicists have designed extraordinarily clever experiments meant to catch nature secretly keeping score behind the scenes, and every time the result is the same. Nature isn't hiding anything. The randomness is genuine. Probability is fundamental. There is no hidden script deciding outcomes ahead of time. This was deeply uncomfortable for many physicists. Some of the sharpest minds of the 20th century spent years, even decades, trying to escape this conclusion. They failed, not because they lacked brilliance, but because there appears to be no escape. This is simply how the universe operates. Physics had to abandon something profound. It had to let go of the idea that we can, even in principle, predict exact outcomes. The best we can ever do, even with complete information, is compute probabilities. That's the limit. There is nothing beyond it. And here's the twist. The framework that embraces this limitation is the most precise theory humanity has ever created, by an enormous margin. Nothing else even comes close. So however uneasy we may feel about probability being fundamental, the universe itself seems perfectly comfortable with it. There's a common assumption that science exists to explain things, that true understanding means being able to say why something happens. But that picture isn't quite right. Science is really about description. It tells us how the world behaves, and it does so with astonishing accuracy. The deeper why questions often don't come with answers. Why does the interaction between light and matter have a strength of 1 over 137? No one knows. Why does probability come from squaring an amplitude? No one knows. Why do the rules of quantum mechanics take this form rather than some other? No one knows. These aren't questions science has simply failed to solve. They may be questions that don't have answers at all, or if they do, those answers may only shift the mystery one step further back. You explain one thing in terms of another, then explain that in terms of something else, and eventually you reach bedrock, a point where the only truthful thing left to say is, this is just the way reality is. You have to learn to live with that uncertainty. You have to genuinely accept not knowing, not in a performative way, where you pretend the question doesn't matter, but in a real way. Because the universe isn't obligated to give us explanations that match our intuition. It doesn't owe us answers that feel comfortable or satisfying. It simply behaves the way it does, and our role is to describe that behavior as precisely as we can. And strangely, once you make peace with that, the oddness starts to feel beautiful. Light taking every possible path at once isn't just weird, it's graceful. The fact that all of chemistry, biology, and material science emerge from just 3 simple actions isn't merely surprising, it's deeply profound. And the most astonishing part may be this. In a universe this strange, the fact that we can predict anything at all is extraordinary. This view of reality, filled with probability, amplitudes, interference, and particles behaving impossibly when no one is watching, didn't come from philosophy or abstract speculation. It wasn't dreamed up through pure reasoning. It came from experiments. People measured the world carefully, got results that refused to make sense, and were forced to invent new ideas just to describe what they were seeing. Nature pulled us toward this picture whether we liked it or not. We didn't ask for quantum mechanics. We didn't want probability to sit at the foundation of reality, but the data left no alternative. And that's the essence of science. You don't get to choose what's true. You follow the evidence wherever it goes, even when it leads somewhere deeply uncomfortable. We now have a framework that works astonishingly well, a framework that reveals light as both far simpler and far more bizarre than anyone once believed. 3 basic actions, tiny arrows, interference patterns. That's all it takes to account for every optical effect ever measured, every color, every reflection, every rainbow, every laser. And yet, we still don't understand why this framework is true. We don't know where its rules originate. We don't know whether they could have been different, or whether some deeper principle forces them to be exactly this way. And maybe that's acceptable. Maybe the most honest position is that we're still in the middle of the story. Science isn't complete. It may never be complete. There may always be another layer beneath the one we understand, another mystery waiting, another question that refuses to fully give itself up. But consider how far we've already traveled. A century ago, we didn't even know that light came in discrete particles. Today, we can predict its behavior with accuracy reaching 12 decimal places. We build lasers, fiber optic networks, and technologies that would have looked like outright sorcery to earlier generations. Reality has turned out to be far stranger than anyone expected. And somehow, despite all of that strangeness, we are beginning to understand it.